Okay, so let me welcome you to this lecture 3 of our course on topics for learning. Today, we're going to review linear quadratic problems that we started on last time, discuss approximation value space for these problems, value iteration, policy iteration, algorithms, and we're going to focus also on visualizations of all these topics and their connection with Newton's method. Conceptually, this is an important part of the course and explains a lot of things that we're going to be discussing. And we're not going to focus so much on Newton's method in the future, but I want you to keep in mind this framework because it underlies an awful lot of stuff related to our subject. Then in the second part of the lecture, we're going to discuss practical problem formulations by dynamic programming, reformulating problems so as to fit the format of dynamic programming or to make them easier to deal with. And we're going to give some examples. And we will continue along this line of reformulations in the next lecture. So here's the outline for today. We're going to review infinite horizon linear quadratic problems with an emphasis on visual representations and explanations. Then we are going to go into approximation value space for these problems with one-step look ahead, again, focus on visualizations. Then we're going to talk about multi-step look ahead and truncated rollout, again, for linear quadratic problems. And after that, we're going to go into the second part of this lecture, which has to do with the art of formulating practical problems as dynamic programming. And we're going to give some examples. And like I said, we're going to continue along this line in the next lecture. Part of this art is the technique of state augmentation that we're going to demonstrate with examples, and also multi-stage, multi-agent problems, which pose a computational challenge within our framework. So let's go into the review of infinite horizon linear quadratic problems. Remember that we have a linear system, A and B are given. I'm taking here deterministic. Everything holds true for stochastic as well, but it's a little easier to deal with deterministic. The cost is quadratic. This Q and R are given, are positive numbers. This is the cost on the state, the cost on the control. This is the cost per stage. We're trying to minimize the sum of all costs over an infinite horizon. J stars of X is the optimal cost starting from state X, and it's given by Bellman's equation. That's a central result. The Bellman equation is what you see here. It involves the cost per stage plus the cost of, as measured by J, of starting from the next state. And it is the limit of the dynamic programming equation as the horizon goes to infinity. And I'm going to call it the min Bellman equation because it involves this minimization over U. And I'm going to contrast it with the L Bellman equation, which has to do with the cost for a given policy, which is linear and specified by a number L, a scalar L. So if I fix L, I get a linear policy from this equation. So the control applied according to this policy is proportional to the state, with constant proportionality being L. So for this kind of policies, there is a Bellman equation that gives as a solution the cost function of the policy. And it's easy to understand. If the control is Lx and you plug it into this cost function, you get this L squared X squared term. And here you get the Lx term. So this is the same as the whatever is minimized here, but instead of minimization, we plug in the value of the control, Lx. And if you solve this by the same reasoning as we had for the min Bellman equation, you get the solution as a solution the cost function of this linear policy. Now, linear policies are important for the linear quadratic problem because it turns out that the optimal policy is linear and everything revolves around linearity. And also a nice thing that's happening here is that these equations, these Bellman equations, can be simplified to what we call Riccati equations. So how do we solve these Bellman equations? Well, we try quadratic solutions, that is cost functions that are quadratic in the state with a constant k as the cost coefficient. We try them in and see if they work, okay, if they solve the problem. And then what's happening is that if I plug kx squared in here, then that would be kax plus bu squared, and this expression becomes quadratic in u. So the minimization of this quadratic expression can be done in closed form. And after I do all that, then I get a solution that has this form with k being this expression, solving this equation here. What's happening also, once I plug in kx squared, then x squared drops out from both sides. So the simplification after I cancel out x squared becomes this equation here. So that's the Riccati equation, the mean Riccati equation. K equals to this, plugging this in, then x squared drops out from both sides, and we get this equation. And this operator here, we call the Riccati operator. It's a function of k, a nonlinear function of k. Now, the L-Bellman equation is obtained from here, plugging in kx squared, and we get similarly this expression. And this is the L-Riccati operator, which is given by this expression. Okay. So how do we solve these equations graphically? Okay, so we plot here the Riccati operator, and it looks like this. Okay, you can verify that this is the form. It's a concave function of k, and it has an asymptote at this point and an asymptote this way. This is a realistic figure, K star is the solution of this, and it is obtained at the point where the right-hand side of the Riccati equation meets the left-hand side, which is this line here. So the solution is right at this point. We intersect the 45-degree line with this graph of the Riccati operator. You can see that there's a unique solution that's positive, but maybe there's another solution also that's negative, but we don't care about that one because our problem, in our case, our problem is clearly positive. And how about the L-Riccati equation? Now, the L-Riccati equation is this: k equals FLs of k, and if we plot the right-hand side, it is linear, like this. It's linear in k, okay? And so we intersect this line that corresponds to the L-Riccati equation and this 45-degree line, and the point of intersection gives you the cost coefficient of the policy, KL. So that's how we obtain the solutions of these two equations. And how do we obtain an optimal policy? Well, there's a theorem that says that if you have a solution of the Riccati equation and you minimize on the right-hand side, then what you obtain is the optimal control, okay? The optimal control for that state. So after you do this calculation here, it is this linear function with L star being this. And what would that be? Well, we know that all these lines correspond to, lie above the red curve. And what we need to find is the line that intersects the 45-degree line at exactly the same point as the red graph. So it has to be this line here. And moreover, this line has to be tangent, because if it's not tangent, then it would cut through the red and get below the red curve, either on one side or the other. So this is a picture. At K star, we sort of linearize by a Taylor series expansion this red curve, and we obtain the graph of the optimal L star Riccati operator. Okay? Is this figure clear? Now, of course, this is a one-dimensional graph because I can only plot in 2 dimensions, right? But the same kind of insights that this graph provides and related insights that subsequent visualizations will provide carry through for multidimensional linear quadratic problems, and also far beyond that to problems involving non-linear quadratic type problems. Okay, so we go to the next slide. Are there any questions? Yeah.
Almost depends linearly on X, right? But why does it depend linearly on K? Why is it linear?
Why is it linear? Well, you see it here. That's the form of this L Riccati operator as a function of K is linear. This is the coefficient of the linear term, and this is the constant.
Yeah, but why also follows the red lines linear?
All the policy, because it is it turns out to be a. Why is the policy linear? Is that the question?
You know, why is it linear from K, not on X? Because
all the policies have linear Riccati operators.
Oh.
All the policies. For any L, this expression here is linear in K. And this is the slope. The slope is A plus BL squared. That's the slope of the line. And the point, the constant, the point that intersects the vertical axis is Q plus RL squared. Okay. And the same is true for the optimal as well. Okay, any other questions? Okay, so this is the solution of the linear quadratic problem graphically. How about computationally? Well, remember, for infinite horizon problems, we have 2 major algorithms, value iteration and policy iteration. Value iteration iterates with the finite horizon costs and applies the Bellman operator multiple times, starting from some initial condition. So now, instead of iterating with the Bellman operator, we iterate with the Riccati operator, and we cancel out by canceling out the x squared terms. So we started with a quadratic. That's the starting point of value iteration. And then we generate successive iterates by using this formula, with this f being the Riccati operator. So from K0, we get K1, K2, and so on, according to this formula. And the sequence of Ks converges to K star. And there's a similar iteration for a given policy with coefficient, a given linear policy with coefficient L. We iterate with the L Riccati operator, starting from some initial K0. So that's the method. And the alternative is the policy iteration algorithm, where instead of iterating on cost functions, we iterate on policies. We start with a linear policy, L0 coefficient, and every iteration consists of 2 steps. Policy evaluation, find the cost function of this policy, and then policy improvement. The policy evaluation of the kth policy, the current iterator, is obtained by solving graphically or otherwise the LK Riccati equation. It's a linear equation. It can be solved graphically or computationally with MATLAB or by simulation, any way you would like. And this gives us a solution KLK. This is the cost coefficient of that policy. And now the next step is policy improvement to obtain the next policy, which turns out again to be linear with coefficient LK plus 1, and is obtained by minimization. The same minimization that you do in Bellman's equation, but instead of J star, you use the cost of the current policy, this KLKX squared. So after we do that, then we have a quadratic problem in U. And after we do this quadratic problem, the result is, solve this quadratic problem, the result is a linear policy whose coefficient LK plus 1 can be calculated in closed form from KLK. So policy evaluation for a given policy solves this equation, policy improvement calculates the next policy with this formula for the cost coefficient. Now, these are the exact forms of value and policy iteration, and we will try to interpret them graphically as well as we go along.
Sorry, what we see is how do we initialize these outputs? What's the initial Q0 of this one?
K0 has to be something that's 0 or positive. And the issue of this initialization will come up in other contexts as well. So I'm glad you're asking this question. As far as the policies are concerned, it is important that you choose the first policy as being a stable policy. Now, we haven't talked about stable policies so far, but we're going to do that in what follows in this lecture. And if the initial policy is stable, all the subsequent policies will be stable, and you will obtain in the limit the optimal solution, the optimal policy.
Yes.
Okay. So, okay, speaking of stable policies, this slide has to do with stability. Okay, remember the Ricciardi equations, the mean Ricciardi equation, the L Ricciardi equation, mean Ricciardi equation, L Ricciardi equation. And now I'm going to focus on the slope of these lines here. The slope of these lines is A plus BL squared, okay? So if A plus BL is absolute, is less than 1 in absolute value, then the slope of this is less than 1. If A plus BL is greater than 1 in absolute value, then the slope is greater than 1. And this kind of line does not cut the 45-degree line, except at some negative value. This one works fine and gives me KL, the cost corresponding to this particular value of L, but this does not give me a solution. Now, what's happening is that this policy is what we call stable, and this policy is what we call unstable. And what is the meaning of stability? Let's consider a linear policy with A plus BL less than 1 in absolute value. Let's look at the closed loop linear system. The control is Lx, so in closed loop, the system is this. If A plus BL is less than 1 in absolute value, then the sequence generated by the system dies down to 0 asymptotically, right? It goes like this, or maybe like this, if A plus BL is negative. Such a system we call stable. if it tends to the origin, regardless of the initial condition and without any control. The control is already taken in through this equation. It's policy Lx. Now, in this case, we have the slope being less than 1. We have a stable system, and the corresponding cost coefficient of the policy is obtained by solving the L-Riccati equation. It's this point here. On the other hand, if A plus BL is greater than 1, then the system is unstable, and the trajectories of this system grow to infinity, either this way or that way. And then the cost of the policy is infinity, right? Because we penalize the square of the state. So if the state goes to infinity, then the cost goes to infinity as well. So we are interested in stable policies, definitely, both from a practical point of view and also from a computational point of view. And we're going to be trying to have this condition satisfied. And as I mentioned in just a little while ago, in policy iteration, we should be starting with a stable policy. Otherwise, the method does not work. Moreover, it's true in general in reinforcement learning that both theory and practical algorithms break down when you have unstable policies. And I'm putting this in question mark because I haven't defined what stability means in a general context. But instability and instability are important in many, many different contexts in reinforcement learning, even in contexts that are not related exactly to system stability. There may be algorithmic stability that may make a method catastrophically fail. And we will see examples of this type later. But to begin with, in control system design, stability is paramount. If you don't get a stable design, then you failed. The first consideration in control system design is to get a stable policy. And that's how we represent stable policies graphically in the context of the linear quadratic problem. Questions here? Okay, so we have L-Riccati operators and min-Riccati operators. How are they related? The min-Riccati operator has this red graph here. The L-Riccati operators lie above that, and they are straight lines. And all of these lines qualify, right, for L-Riccati operators. And it turns out that if you take the lower envelope of all of these blue lines, you get the red curve. And how can we see that? Let's look at the right-hand side of Bellman's equation and the min-Riccati operator. It involves this minimization with respect to u for a given value of k. Now let's do the following trick. Break down this minimization into two minimizations. First, minimize over all u that are equal to Lx for a fixed L, and then minimize over L. And I can do this inner minimization in closed form. And what I get, you can see the algebra here, is put Lx here, and then do the minimization. You get exactly the L-Riccati operator with x star coming, factoring out, cancel out x star on both sides, and what you get is this. The min-Riccati operator for a given k is the minimum over all linear policy coefficients of the L-Riccati operators. So what this says is that this red curve is the minimum of all these FL lines. Okay. Here's another thing that this equation says, that if I have some k over here, and I want to find f of k, I can do it by minimizing over all these values, over L. So I can go at this vertical line and look at all these points where these lines intersect. And then I can take the lowest line. And that lowest line, this one here, has to be tangent, okay? So this lowest line, which defines the value of the mean Riccati operator, is a linearization of the mean Riccati operator. And that's going to be important for what's coming. So let's try to interpret approximation in value space in terms of linearizations and also in terms of Newton's method. And we're going to focus on one step look ahead first. Okay, what do we mean by approximation in value space? Remember this figure that we had at the very first lecture. We are at a given state. We look at all possible choices of control, all possible next states, and then we approximate the cost to go from these states with some j tilde function. And in this particular case, we're going to look at quadratic cost approximations that involve a k tilde positive coefficient. So this is now this k tilde may be obtained in a number of ways, offline training or light forms of online training, like training a heuristic policy or something like that. We don't care really how we obtain k tilde. Somebody gave us to start the online play algorithm, which does this minimization. Now, the online play algorithm, I will show you that it is a Newton step aimed at solving the Bellman equation or the Riccati equation because X star factors out. But what do we mean Newton's method? Okay, how many of you are comfortable with Newton's method and know what it means from calculus? Question. Okay, most of us do, right? Because most of us certainly have been exposed to it, but perhaps we may not remember it. Newton's method is one of the most fundamental methods in numerical analysis. It's used to solve equations, one-dimensional equations, or multidimensional nonlinear equations, or it may be used to solve optimization problems. And it's the most powerful method. The fastest method among all numerical analysis methods for solving equations is Newton's method. It has what's called superlinear convergence. Once it's close to the solution, it just zooms in. It takes like 1-2 iterations and you're done. You found the solution with great accuracy. It's extremely powerful. On the other hand, Newton's method has some drawback, namely that you have to start it reasonably close, within its region of convergence to the solution. Otherwise, it may diverge unless modified. So also Newton's method can be solved for solving fixed point problems of this form. Y equals g sub y. G is some nonlinear function, which I'll assume is differentiable. Why is that? Well, a fixed point problem is really an equation problem, right? I just taken y to the left-hand side. So I'm going to give you Newton's method for one-dimensional problems for this fixed point problem. So here's the mapping G, and you can think of the Riccati operator if you will, but here I'm being general. And the solution, which I call y star, I use the term y. I don't want to use k because I'm going to talk about in generic terms in this slide. So the variable is called y. And the solution y star is given at the point where the right-hand side, the red curve, meets the left-hand side. So this is a solution. There's also another solution over here. But let's look at this solution here. And let's see how Newton's method works. It's an iterative method. And at the kth iterate, the current iterate, it linearizes the problem with a first order expansion of G, a first order Taylor series expansion. So at this point, we linearize this G, okay? And the slope of this is just the gradient of G at yk, right? And now that we have this linearization, we can look at the linearized problem, which is the problem where G is replaced by its linearization. So the linearized problem is the point where the linearization meets the 45-degree line. It's this. And that's the next iterate of Newton's method. From yk, it generates yk plus 1 by solving the linearized problem instead of the original. And then at yk plus 1, it relinearizes and goes to this point, yk plus 2, relinearize again. And it is evident from this figure that you converge very, very fast if you happen to, if once you get close to y star. On the other hand, if you start far away from y star, if you start right over here, you linearize and the slope here, suppose it's greater than 0, then the point of interception is away from y star, and you don't converge, you diverge rather from y star. And there's a certain region that is the region of attraction of a particular solution, where if you start Newton's method within this region, then you eventually converge, and you eventually converge very fast. On the other hand, if you start away from this region of attraction, then you have a problem in that you may not diverge. So that's the general intuition behind the region of attraction, the convergence, and the operation of Newton's method. And let me also point out that Newton's method extends very broadly. It applies to multidimensional problems that are differentiable. It applies also to multidimensional problems that are non-differentiable, where G has corners. Then the question may arise, what is the linearization? Well, it turns out that instead of using gradients, you use something called a subgradient, which is just a hyperplane that it's a hyperplane that supports the graph of the function. There is an easy way to understand Newton's method for non-differentiable problems if you apply it to the case where the right-hand side is the minimum of several differentiable functions. Then you use the gradient of whatever differential function is active at the current point. And there's an explanation of all this in your textbook, but I don't want to go into that because that will detract us from we'll get into mathematics and that will detract us from our main objective. But Newton's method generalizes and it's applicable very, very broadly within our context, even though we are going to demonstrate it for the case of linear quadratic problems where everything is nice. So now in the next slide, I'm going to show you how approximation in value space is Newton's method, a step of Newton's method. Are there any questions here? Okay, so that's what we want to do. We want to visualize approximation in value space with one step look ahead and no rollout. We're not going to use any rollout. So here's the Min-Bellman operator. And suppose that we approximate the cost to go with K tilde X star. We got this somehow from offline training or whatever other method. And what we want to do is approximation in value space. Well, what we want to do is minimize, is find a policy that minimizes for this k tilde. And what we need to do then is for all the possible policies, find the one that comes the lowest, right? According to this minimization. And so we look at all the crossing points of the linear graphs, and we find the one that's lowest, and that one has to be tangent. So the graph of the minimizing L policy, or the L-Riccati equation, is given by this tangent, and the cost of that minimizing policy is given by the point of interception with a 45-degree line. So you start with cost approximation k tilde, and you get a one-step look-ahead policy, KL tilde, which is obtained by this linearization construction. So what is this? Well, it's exactly Newton's method. Starting from k tilde and going to the cost of the one-step look-ahead policy is a Newton step. Exactly. Now, what's the consequence of this? If this k tilde is close to k star, then this is going to be very, very close to k star. There's a huge improvement in cost. If k tilde, on the other hand, is not very close to k star, in particular, if it lies outside the region of attraction of Newton's method, or the region of stability that we called it earlier, then this process does not work, breaks down. So that's the Newton step interpretation. Questions here?
Maybe I'm wrong, but why isn't it inverse? If you go, I was trying to work with myself, but shouldn't the gradient be inverse in the Newton method? If you go to the previous slide, I mean, there was delta G, like it was the gradient, but from what I know, usually the 1 over the gradient, right?
That would be another way to carry Newton's method and would be equivalent. What we're doing here, we are using Newton's method through approximation in value space. And our objective is not so much to carry out Newton's method in the best way possible, if there is such a method. Our objective here is to visualize what approximation in value space does.
Okay.
So this is not a method of solution. This is a visualization, an interpretation of what is the cost of the one-step look-ahead policy and how is it related to the cost function approximation.
But is it possible to slide 11? Because I wanted to ask a question before, but I wanted to just check my work before. I just want to know whether like the equation is exactly correct or the g of y is actually, isn't it? So there was delta g of y. That's not like 1 over, because like, I know Newton's method to be like xk plus 1 plus xk minus f of x over f of x prime.
Yeah.
But there is no.
That's exactly what this is.
But what is the inverse on the derivative?
Look at this equation here. To solve this equation, you have to solve for yk plus 1.
Oh, okay, yeah, it's not the finite form. Yeah, okay, now I'm.
So that's how you invert. That's where the inverse comes in.
Yeah. Okay. No, I see now. I think because I didn't see that you kept yk plus 1. I thought, yeah, no.
Okay. Okay, fine. Okay, so this is the interpretation of one approximation value space. We linearize, and then we obtain the cost of the one-step look-ahead policy exactly as in Newton's method. And that's the critical connection. Okay. So now let's also visualize the region of stability in approximation in value space with one-step look-ahead. Suppose that I take my K tilde somewhere in here. Let's say you take a K tilde to the right of K star. Then the corresponding policy is going to have this. Then the corresponding policy is going to have slope less than 1, and it's going to be stable. Also, if K tilde is in this region, then the tangent is going to have slope less than 1, and again, it's going to be stable. On the other hand, if you go to the left of this point, which corresponds to slope equals to 1, and you use a K tilde within this region, then you're going to get an unstable one-step look-ahead policy, and then you're going to have difficulty. So this Newton step interpretation and visualization shows you how instabilities can occur and defines also the region of stability as being to the left, to the right of the point where the slope is equal to 1. And for the method to be successful, the start of the Newton step must be within the region of stability. And characterizing the region of stability becomes an issue that's important within the context of linear quadratic problems. Now let's also try to visualize rollout with a stable linear base policy. Remember what rollout is. We introduce a base policy which has cost function J mu, and we use as cost function approximation the cost of that policy. We use this J tilde here. Now I'm going to choose the base policy to be stable, so its slope is going to be, the slope of the base policy is going to be less than 1. So it intersects the 45-degree line, and this is the cost of the base policy. Now, rollout is approximation in value space with this cost function approximation, and it is given by linearization and a Newton step, and that gives you the cost of the rollout policy. So here's the cost of the base policy, here's the cost of the rollout policy, and it's given by an exact Newton step. And because we have Newton's method that's very fast, this new policy, the rollout policy, is much better than the base policy, particularly if the base policy is relatively close to K star. Notice also that this particular approximation in value space that involves KL or J, as J till J mu is an approximation to the right of K star. And because of the way this concave curve is sloping, the approximation from the right, the Newton step from the right tends to be more effective than a Newton step from the left. So the rollout policy, the base policy is a good starting point in the sense that it's to the right of K star. Moreover, you can see from this figure that if the base policy is stable, so that it gives you some point to the right of K star, then the rollout policy is also stable. You can play around with this and see that this is true. Not only a better policy, but also a stable policy. Okay, there are a number of ways to see that. Okay, from this figure, but the important fact is that if you start with if you use rollout with a stable policy, then you're going to get a stable one-step look-ahead policy, and that's important for the point of view of application. Is also important in the context of policy iteration, because policy iteration is a repeated rollout. So if you start with a base policy that's stable, the policy iteration, then all the subsequent policies are going to be stable. Questions here? Okay, so covered a lot of figures. Let's take a break here, and then we'll continue with multi-step look ahead and how we interpret Newton's method and approximation in value space. Okay, let us get started. We talked about one-step look ahead and the interpretation, the Newton step interpretation that maps from the J tilde approximation into the cost function of the one-step look ahead policy. So with one-step look ahead, what we do basically is minimization with some cost function approximation at the end to approximate the optimal cost. Now, in multi-step look ahead, we have multiple levels and steps of minimization, and the figure becomes like this. This shows two-step look ahead minimization. At the current state, we look 2 steps ahead at all the possible states that can occur, and then we take a cost function approximation, which may be preceded by truncated rollout. And the cost function approximation for the linear quadratic case is quadratic, given by this K tilde. So this is the same figure, except it has an extra layer of look ahead and also this truncated rollout. So the one-step look ahead is applied to everything that follows after this point. So this is a Newton step applied to the function that you obtain after you lump all these steps together. And what these are, there's one value iteration here, multiple value iterations in the case of look ahead of more than 2 steps. There's also some other stuff here, and there's also cost function approximation. So the interpretation that we are going to give is this general scheme involving multi-step look ahead and perhaps other stuff is a Newton step, but applied to something different than J tilde, something that has hopefully been enhanced. And these extra steps here serve to bring the cost function approximation closer to J star and perhaps into the region of stability so that Newton step can be effective. That's the whole idea that I'm going to try to get across to you. Multi-step look ahead is the same as one-step look ahead, but with a better starting point. And this better starting point is affected through extra layers of look ahead minimization and also look ahead with a policy as in truncated rollout. Okay, to understand this value iteration that I mentioned here, let's try graphically to look at value iteration for linear quadratic problems. Okay, so value iteration iterates on cost coefficients from kk to kk plus 1, kk plus 2, and so on, according to this equation, which uses the Riccati operator to map kk into kk plus 1. And this comes from value iteration with cost functions, except that the x squared fact has been factored out from both sides. So in terms of the Riccati operator graph, value iteration is an iterative method that at the typical step has a kk coefficient, finds kk plus 1 by f of fk. So this is kk plus 1. Then we take this and we reflect it across the 45-degree line. Here's kk plus 1. And then we take as kk plus 2 the value of the Riccati operator at this point, and so on. So value iteration in this graph here is interpreted as a staircase ascent towards the K star. You can see that for any positive starting point or zero, or even some negative, you're going to end up converging to K star through this staircase operation. And the same is true if you start from the right, because the staircase operation is going to go like this. And in fact, it's going to be even faster from the right. So that's how value iteration works. And it helps to bring some starting point closer to K star. The more value iterations you apply, the closer you're going to get to K star. So now going back to two-step look ahead and multi-step look ahead, let's try to visualize that. In approximation in value space, we have a cost function approximation, this K tilde. Now, in two-step look ahead, we first apply a value iteration to that, and the result is where the first step of look ahead minimization is done, which is a Newton step. So instead of going here and then taking linearizing, we do a value iteration first and then linearize. And that gives us the cost function of the look ahead policy, the two-step look ahead policy. It is a Newton step, but not starting from K tilde, starting from the point K1, which is an enhancement of K tilde. It has been enhanced by a value iteration. In three-step look ahead, we would have start with K tilde, do one value iteration, then a second value iteration, and then apply the Newton step. So it will work better because the starting point for the Newton step is going to be better, closer to K star. So this brings up a general idea that the longer the look ahead, the better. And even though I'm not showing rollout in this figure, rollout also helps. And you can draw the corresponding figures and see how it works. All of this is important. And another important point that I want to make is that multi-step look ahead improves stability. Suppose that you start, for example, from some cost function approximation that gives you an unstable policy. Then you're in trouble. On the other hand, if you use two-step look ahead, the next step, which the first look ahead step brings you to a point which may give you a stable policy. In other words, extra layers on look ahead bring you closer to K star, which can bring you within the region of stability of the method. So that's an extra benefit of multi-step look ahead. Not only better approximation of the optimal policy, but also improve stability. It can succeed where one-step look ahead can fail because we don't have a good enough approximation. Multi-step look ahead enhances the cost function approximation, brings it within the region of stability, makes the method work. That's again a general insight within reinforcement learning. Longer look ahead helps. Of course, longer look ahead also costs more computation time because you have to, solve more difficult problem, more difficult minimization problem at every step. Any questions with this? By the way, your next homework is going to be playing around with figures like that. So I hope that this will help understand some of the finer points that may not be evident. Okay. So let's now go to policy iteration for linear quadratic problems. We mentioned rollout. It's one Newton step starting from the cost function of the base policy. Now, policy iteration is simply a repeated rollout. Get a sequence of policies, each one with a better cost, starts with some linear policy, generates a sequence of linear policies involving cost coefficients LK, with a two-step process of policy evaluation and policy improvement. Both of these can be done in closed form in the case of linear quadratic problems, a very simple case, of course. The policy evaluation is done by solving the LK Bellman equation to find this coefficient here in closed form. I'm sorry. For a given policy, LK of X, policy evaluation gives the cost function of the policy by solving the LK Riccardi equation in closed form. And this is the solution as a function of LK. Policy improvement gives you a new policy with cost coefficient LK plus 1 and uses KK from the cost evaluation and this formula here, which comes again from quadratic cost minimization, the formula for policy improvement. So the formulas here are not important to remember, but what's important is that they can be done and they generate linear policies in closed form, essentially. A single policy iteration is what rollout is, and it's a single, and it can be viewed as a single Newton iteration. The policy iteration method is repeated rollout, and it's a full-fledged Newton's method for solving the Riccardi equation, with every iteration being a rollout step. And it will asymptotically solve the Riccardi equation, but much faster than value iteration. That's another important point. Policy iteration is much, much faster than value iteration. Particularly once it gets close to the solution, then one iteration gives you almost the exact solution. There are a lot of variants of policy iteration. They admit graphical interpretations. One of them is called optimistic policy iteration, where you evaluate the current policy approximately by using some value iterations. And this is the essence of truncated rollout. It can be viewed as an approximate or optimistic policy iteration with inexact policy evaluation through some value iterations. And it can also be viewed as what's called in numerical analysis a Newton SOR method. A Newton SOR method for solving equations consists of a repeated application of a Newton step, but each Newton step is preceded by first-order iterations like value iterations. So do a number of value iterations and then a Newton step, a number of value iterations and a Newton step. That's the essence of this optimistic policy iteration. And it's an important method within the context of reinforcement learning, because very often we cannot do rollout exactly. We have to deal with approximations. Have a question? Yes?
Is there a guarantee that for LK, A plus B, LK plus 1 will be smaller than 1? Because this equation doesn't constrain that. So how can you guarantee that A plus the absolute value of A plus LK plus 1 times B smaller than 1?
Okay, so the starting policy for policy iteration has to be stable.
Yeah.
If it's stable, then all the subsequent policies will be stable. That's a fact that you can prove, and it's easily seen both graphically and also analytically.
As long as you are like, as long as we follow this update. Okay.
Yeah, these updates guarantee the stability of all the policies if you start with a stable policy. If you don't have a stable policy to start with, then you're in trouble. Okay, so let me also mention that there's a broad generalization of all these graphs that I gave you and all the ideas behind them. And they generalize very broadly to essentially arbitrary dynamic programming problems, both deterministic and stochastic, both finite horizon and infinite horizon. Because dynamic programming ideas do not really depend much on the state space that you use or the control space. They apply in great generality. And this generality passes through to this Newton step interpretation. However, the mathematical analysis to establish all that, in other words, from intuitive visualizations to go to rigorous mathematical results, that requires analysis that can be substantial. But this analysis has been done, okay? And you can look at your textbooks and also the references in your textbooks to get into, to get the full range of results of this type. And just as an outline, in a generalized view of approximation in value space and Newton analysis, Riccati operators have to be replaced by Bellman operators, general Bellman operators. Newton's method for solving the min Riccati equation becomes Newton's method for solving the min Bellman equation. A mathematical point that I alluded to a little earlier, that non-differentiability of the Bellman operator, it's not differentiable because it's the minimum of several linear functions, basically, and it can easily be non-differentiable. However, this is not an issue because there is a form of Newton's method that can deal with non-differentiability of the Bellman operator. And you can look at your textbook, and there's an appendix that explains this in greater detail. All of this takes us to substantial mathematics, okay? So, but those of you who are PhD students and want to look more deeply into research in this area, it's the kind of mathematics that are worth looking, are worth becoming familiar with. In general, approximation value space is a single Newton iteration, but enhanced by multi-step look ahead, if there is multi-step look ahead, and by truncated rollout, if any. In other words, the picture is we have a single Newton iteration, but the starting point of the Newton iteration is enhanced by good cost-to-go approximation, by multi-step look ahead, and by truncated rollout. The rollout itself is a single Newton iteration, provided the cost evaluation is exact. Exact policy iteration is a full-fledged Newton's method. And a key insight is that multi-step look ahead and truncated rollout enhance the stability properties of the policy produced by approximation value space, and also leads to more stable methods that tend to work in spite of the many approximations that you may make in their implementation. Of course, multi-step look ahead costs a lot of computation, and that's the trade-off: better performance versus increased computation. So that's all I have to say about these visualizations and Newton's method and the approximation value space. Now we're going to go into the issue of how you formulate problems, practical problems, as dynamic programming problems, and by extension as reinforcement learning problems. So how do you do that in practice? Well, there's no unique answer, but here is the recipe that I suggest. The first thing, that given a practical problem that you want to address through dynamic programming and reinforcement learning, you first define the controls. You first define the actions. These are easy to figure out. You have a sequence. If you have a scheduling problem, the controls are the scheduling decisions, right? Once you have the controls, then you can look at what kind of information is available at each stage and when it is available, and that defines the stages. And one way to look at how you divide the horizon into stages is to look at the points where the information becomes available, because that's when you want to apply controls. The third thing that you want to figure out is what are the states? And when it comes to states, there are many different formulations. You can choose many different things as states in practice. Now, there's one important guideline here. Define as state something that summarizes the past for the purposes of future optimization. So that as long as you know the state, everything that has happened before that state happened is irrelevant. All the past is irrelevant given that we know the state. So that's how you recognize states as the essential information for the purposes of future optimization. And the rationale is that the controller applies action that depends on the state. So the state must subsume all the information that's helpful for decision and control. And so that's the way you look into problems. On the other hand, subsuming all information that's useful to control can be done in many different ways. You can encode the information that's important for control in many different ways. So let me give you some examples. Let's consider the traveling salesman problem with which you are familiar. We need to include in the state all the relevant information. That would be the current city is certainly an important thing to know when you apply a decision to go to the next city. And you also need to know what the past cities that you visited are, because that's how you know what your options are for the next city. Now, other information, such as the cost of visiting previous cities in the tour, they don't matter. They are not important, and they need not be included in the state, although technically they could be. Now, here's another important example that we are going to discuss in the next lecture. It has to do with partial information problems, where the controller does not know xk, but rather receives measurements about the value of xk. So we use noisy measurements for control of some quantity of interest. We call it yk, and which evolves over time, like the position velocity vector of a moving state. Moving object, something that you would take as state had you known their exact values. But if you don't know these exact values, then it is correct to use the measurements in place of those. All the information that you have up to that time, that would be the state. That would be the state of information. But there's an alternative also, which is some kind of probabilistic state. It's possible to use the conditional probability distribution of the quantity of interest given the information. In other words, instead of using IK as state, which may be difficult to deal with, you may use a probability distribution over the quantity of interest given the state. That would also be a legitimate choice for state. In the POMDP literature, the partial observation state literature is called the belief state, some kind of probabilistic state. It subsumes all the information that's useful for the purposes of control choice, but it is in a probabilistic form. So the choice of state arises here, and there are several different concepts of state that can be useful. So of course, this requires some reformulation of the problem. From states, you may go to probabilistic states, you may go to belief states, you may go to information states, and so on. And let's look at reformulations now from another point of view. Okay, there's a general technique called state augmentation, which I'm going to illustrate by example. It is helpful in taking a problem that's not exactly in the form that you can use to apply dynamic programming, but it reformulates it to one where you can write a dynamic programming algorithm. And here's an example where the system equation involves delays. So the next state depends not only on the current state and the current control and perhaps some noise, but also on the preceding control that you have applied and the preceding state that you were. So there's a delayed effect on the next state. This is what we mean by the system equation involving delays. So how do we deal with that? Well, the idea is to take a state, everything that is important for the purposes of future optimization. When we choose UK, it is important to know this. It's important to know that because that affects the next state. So it is natural to think about introducing additional state variables that encode these delayed quantities. And we can write a system equation for those. Yk plus 1 is equal to xk, according to this definition. Sk plus 1, the delayed control at the next stage is going to become the current control. So technically, we have a system equation that involves an enlarged or augmented state that involves xk and also the delayed quantities. And we can write a system equation that's basically this equation here. We write it like so. It involves the current augmented state, the new augmented state, the control, and the disturbance also. And F tilde K is the mapping that corresponds to these expressions here. So now, once we have done this reformulation and we have a cost function, we can write a dynamic programming algorithm for this augmented problem, augmented system. The dynamic programming algorithm starts from the terminal state as usual, and then at the typical step, the optimal cost to go at time k depends on the augmented state, which is xk, xk minus 1, and uk minus 1. It's a bigger state. And the equation is what you see here. It makes sense. Expected cost of the current stage plus expected optimal cost to go. That depends again on the augmented state. So this is a legitimate dynamic programming algorithm, except it's carried out over larger space. The space not on just xk, but also xk minus 1 and uk minus 1. And the more delays you have, the bigger the augmented state can be. You may have problems where the dependence of where the current state depends on all the previous states. Then all of these previous states can have to be included in the augmented state and in the dynamic programming algorithm. This type of state augmentation has a very large range of applications. Is the go-to tool when you have a problem that doesn't quite fit exactly the dynamic programming framework. You look for some kind of state augmentation. And there are different types of state augmentation. Your textbook has some other examples. For example, forecasts of future uncertainty. Suppose that you are at time k, and all of a sudden you get a forecast that let's say the demand for your product in 1 month is going to be 3 times bigger than what you expected. Then you have to include this information as part of the state. This forecast has to be part of the state because your control, your decision is going to depend on that. So there are many examples. You can look at all of this. The general idea also here to keep in mind is that state augmentation is a very powerful and general reformulation tool, but also results in dynamic programming algorithms that can be very, very costly because of this size, the increase in size of the state. Okay, another type of reformulation. Many times you have a problem where there is a termination state or a goal state that you're trying to reach. like for example, in shortest path problems, you try to reach a certain destination, or in games like chess, the problem stops when you reach the end of the game. And so, of course, you don't know, you don't have a fixed horizon exactly when the game is going to end, but there is this termination state. Now, dealing with such problems can be done in several ways. One possibility is to view them as infinite horizon problems, even though you expect that you're going to terminate in a finite number of steps. And that may be a matter of convenience or a matter of, there may be some conceptual value to it. And you can do this transcription from essentially finite horizon problems to infinite horizon problems by introducing an additional state corresponding to termination, to which once you transition, you just stay there forever and ever. So that's one possibility. Every finite horizon problem, or every problem that you are going to terminate within a finite number of steps, you can also view it as an infinite horizon problem with an extra termination state, and then you can make use of infinite horizon ideas, infinite horizon algorithms. Another possibility is to convert it to a finite horizon problem, assuming that you know an upper bound to the optimal number of stages. If you know that the optimum is going to occur within 100 stages, then you can consider it as a problem with 100 stages or 150 stages or 1,000 stages. And then you can add a big penalty as terminal cost for not terminating, not reaching the termination state at the end of the horizon. That's a possibility also. Now, let me give you an example of a problem with a termination state. Here you have a graph, and you have two vehicles moving one step at a time within this graph. And the objective is to perform some valuable tasks that are located at particular nodes. Once a vehicle gets to such a node, then it performs the task. And the objective is to perform all the tasks and to do it, as an example, in a minimum number of steps, minimum number of moves. Now, at every time step, there is a move by both vehicles to a neighboring node from where they are. So, okay, so we have the laws of evolution of the state. We don't know what the state is. We have a cost function, but how do we formulate this problem as dynamic programming? What would you take as states? Any ideas? What would be important at any given situation for the purposes of future optimization? What would you like to know? What would you need to know? Say it again.
Where the two vehicles are.
Where the vehicles are certainly should be part of the state. Is there any other component of the state that you would include? The number of moves taken. I can't, no, that would not be part of the state. How many moves it has taken you to be where you are, that would not be important for the purpose of future optimization. It would affect the overall cost, but not the future costs. Okay. How about the list of the tasks that you have already performed? Okay. I mean, that list would be important to direct you into completing the remaining tasks. So it's an important piece of information to have in a dynamic programming problem formulation. So a good state here would be the position of the vehicles at the current time and also a list of the tasks that you have already performed. And there's a termination state. What is the termination state? It's the state where all the tasks have been performed. That's a termination state. And then you can view this as an infinite horizon problem, if you wish, where you stay at that state with no cost incurred in the future. But you can also view it as a finite horizon problem. What would you take as a horizon here if you wanted to formulate this as a finite horizon problem? The number of nodes in the graph? It's not the number of nodes in the graph. Okay, it's an estimate on the number of steps that you need optimally to do all the tasks. So here you can look at this graph, the optimal solutions marked in red here, in 3 steps. You can perform the task if you act optimally. Of course, you can act non-optimally, and you can go around a roundabout way to get to this task. Or maybe even if you want to be really stupid, you can just go back and forth and waste time and do nothing. So in principle, there are policies that can have an infinite number of steps. However, the optimal number of steps here is 3. If you take a horizon 3 or more, then that would be a correct reformulation of as an infinite horizon problem with a penalty for not terminating within 3 or whatever steps you set as horizon. It's also possible to estimate the number estimate an upper bound to the number of steps that you would need. Okay, there are 2 tasks here, and you would need no more than 12 steps for one vehicle to get there, okay? So multiply that 12 with the number of tasks, that gives you an upper bound. That would also be another possibility. What's the control space here? What's the action space?
You would have to take the cross products of like both vehicles' possible actions.
Yes. Yeah, the vehicles move simultaneously, so you would have to take all the pairs of moves, all the possible pairs of moves. In general, if you have n vehicles, you would have to take all the Cartesian product of n of the moves of the individual vehicles. So what does that do to the control space? If you have, let's say, 10 vehicles, and each one has 2 options to move in every step, it's 2 to the 10th, right? You have 500 vehicles, each one with an option of 2 possible moves, it's 2 to the 500. The search space increases very rapidly with the number of vehicles here. And the size is astronomical, even for a modest number of tasks and vehicles. Now, to deal with this, there's something that we're going to deal with in some detail called multi-agent rollout. A form of rollout that deals with multi-agent problems involving multiple independent decision makers, with the result that the joint decision becomes very complicated and very large. So let's talk about multi-agent problems now. It's a popular class of difficult problems. It's also an old type of problem. It dates to the 60s. And it relates to a situation where you have multiple decision makers or agents collecting information from the environment and sharing information selectively with each other. And agent I applies decision UI. So U1, U2, U3, and so on. And the collective decision is this M component vector involving the choices of all the agents. Now, this is a difficult problem, a difficult class of problems, but there is a major mathematical distinction that characterizes the difficulty of the different problems of this type. It has to do with information, how much information these agents have. There's the classical information pattern where the agents are fully cooperative. They're not fighting each other. They don't have different objectives. They work for the same purpose, and they fully share information, and they never forget the information that they have got. Now, this is the easier type of problem because it can be treated as dynamic programming, as I'm going to show in the next slide. The other possibility is to have a non-classical information pattern where the agents are only partially sharing information, so they act without common information, and they may also be antagonistic. They may have different objectives. Now, this is a hard problem, very hard class of problems. And the reason is that it cannot be treated by dynamic programming. To give you an idea of how hard this type of problem is, I worked on this 50 years ago, more than 50 years ago, when I was a PhD student. I spent about 6 months looking at these problems because they were very old, okay? They date way back. And I realized after 6 months that I was never going to get a good, clean result in this area, and I switched to research areas. So these problems are notorious for their difficulty, but people are still addressing them and with renewed interest because we have now new methods and more computation at our disposal. So it's an important subject for research in reinforcement learning. There are lots of methods, some of them very crazy methods that people try, and some of them very misguided, but it's a subject of great interest. So what are we going to do with this class of problems? Well, we're going to look at the easy case first. The starting point is going to be the classical information pattern, but later we're going to try to go into the non-classical information pattern case. Now, the classical information pattern, where everybody shares all the information and everybody communicates their controls and coordinate their controls, can be visualized and can be conceptualized in terms of an information and control cloud. It's a cloud involving a central decision maker that collects all the information from the agents, collects all the information from the environment, does all the computation, and sends back to the agents the controls. So this becomes a dynamic programming type of problem solved by the cloud. And it could be stochastic. It has a state and a control U, which is the Cartesian product of all the controls, the M tuple of controls of the agents. And let me also note that agents here is just a metaphor. These agents could be distributed over a geographic area, or they could be housed in a single computer, okay? They may be parts of a robot doing different things, having 2 hands, 2 feet, and other things. And you can view the hands and the feet as agents because they require decisions that are separate. And the theoretical framework that we're going to use is dynamic programming. And we will reformulate dynamic programming and other approximate dynamic programming methods so that the computation becomes faster and we're able to deal with this enormous control space. So we'll deal with this exponential size of the search control space. And later we're going to discuss how to compute the agent controls in a distributed fashion so that the computation becomes faster. And also in the process, we will deal in part with non-classical information pattern issues. Now let me illustrate this with an example, and you may ask, save your questions for then. Okay, so this is a cute example, and in fact, a number of students in past offerings of the course have chosen it as a vehicle for a term paper or a project. It's typical of problems in vehicle routing, in maintenance, search and rescue, firefighting, a lot of different practical contexts, but we're going to describe it in terms of spiders and flies. Here we have 15 spiders moving in the 4 directions within a grid, or they may stay at any given time step where they are. And there are 3 flies, and the spiders are trying to catch the flies. And the spiders have perfect vision and share perfect information. They know where the flies are, and they also know where the other spiders are. And the flies, on the other hand, are blind. So they just move around and, okay, so they're passive. And the objective is to find a strategy for the spiders so that they catch the flies in minimum expected time. So now, what's the search space here? How big is it? Each one of those spiders can move in the 4 directions or stay where it is. So it has 5 choices at every time step, except if it is at the edges, it has less than 5, but let's say 5. And there are 15 spiders. So the number of all possible joint moves is 5 to the 15 or thereabouts, right? There are 15 of them, each one. So the control is a 15-dimensional vector. Each one component can take 5 different values, 5 to the 15. Now, we're going to look at rollout algorithms that will reduce the number of choices to 5 times 15, a much smaller number, while still maintaining the good properties of the rollout framework. And the idea is to break down the control into a sequence of 1 spider at a time moves. So 1 spider moves, tells what it has done to the other spiders, the second spider moves, then the third spider moves, and so on. So each one has to choose between 5 different choices, and 15 of them have to do it in sequence. So it's 5 times 15, choice between 5 times 15 choices that we have to calculate. And there's more discussion in your textbook, and there's also some videos on the internet, and you can look into that. So what I said is that there's a lot of reduction in the computational load while maintaining good properties. And let me explain why this is so. There's an old theoretical idea going back to the neurodynamic programming book of 1996, which reformulates the problem by unfolding the control action. Now we're talking about a general multi-agent problem where the control space is the U is consists of components U1 up to UM. Now in the standard formulation, we go from a state to the next state according to a system equation. It depends on X, on U, and on W, and there's a cost corresponding to this transition. Now, U consists of the M components, and we're going to break down its choice to one at a time. So we're going to introduce additional states, like state augmentation. From X, by choosing U1, we're going to go to state XU1 at no cost. Then we're going to choose U2 and go to this state here, again at no cost. At every stage, we're going to make one decision up to the last choice, where the state is the current X and also all the controls that have been chosen up to this time. And we choose the last control, completing the choice of U, in making this transition and incurring this cost. So it's one step at a time. And in this way, the control space has been simplified tremendously. There are only a few choices to be made at every step. On the other hand, the dimension of the state space, the size of the state space has also increased tremendously. And if you try to apply dynamic programming within this formulation, you'd have to deal with cost-to-go functions that have much larger dimension, right? Depend on a lot more arguments. So this idea is not useful at all if you want to do exact dynamic programming. However, it is useful if you want to do approximations. Approximations that do not like large control spaces, but are not bothered by large state spaces. And rollout is one of those. In rollout, you only look at the current state. You don't look at all the possible states. The computation involved only the current state. And so rollout is not affected by this increase in size of the cost-to-go functions. On the other hand, rollout for this problem, well, this problem is equivalent to the original. Rollout one agent at a time, where you choose U1 and the remainder is chosen according to a base policy. Then you choose U2 and the remainder is chosen to a base policy, but what you've chosen before is still, you know what you've chosen already. So this is a different form of rollout, but it is the standard rollout for the reformulated problem. As a result, it has the Newton property. It really implements a Newton step. And that makes this operation just as good, of this type of rollout just as good as the rollout where you would have to deal with a larger control space. Okay, it's not going to be the same rollout policy that you're going to get, but you're going to get a policy that could be better or it could be worse, and generally is in the same ballpark. So essentially, when it comes to rollout, by unfolding the control space, there's an awful lot to be gained and very little to lose, if anything. It's a really very effective type of reformulation and very effective algorithm. We're going to give examples of this. We're going to elaborate on this point, give case studies and so on. The computational evidence supports very much what I've stated here, what I've said here. So that's what this bullet says. The increase in size of the state space does not adversely affect rollout. Only one stage and its successors are looked at each stage during online play. And if you do a complexity calculation, the one-step look-ahead branching factor is reduced from n to the m, okay, to n times m, where n is the number of possible control for each component. So at every step, you have a branching of at m steps, so m steps at every step, at every state, and that amounts to n times n complexity of calculations, and a huge reduction from an exponential complexity of n to the m. So we're going to return to multi-agent problems and multi-agent rollout. and also the issue of non-classical information, problems with non-classical information patterns when in some future lecture. Are there any questions here? Okay, so we've reached the end of this lecture. And in the next lecture, we're going to discuss reformulations again, including more problem domains, like POM-DP, partial observation, Markovian decision problems, adaptive control, and model predictive control. And there will be a homework due in 1 week, which is exercise 1.2 of the latest version of the class textbook. Last week, I downloaded a new version that involves edits, and it includes an exercise, this exercise 1.2, which is your homework. And this exercise deals with linear quadratic problems and the type of visualizations that we did in this lecture. Please read ahead. We're going to be staying with section 1.6 of the textbook. And the next lecture is going to mark the end of the 4-lecture introduction to the course. After the 4th lecture, we're going to get into more specific topics in greater depth. Everything up to the 4th lecture is going to be a foundational review. And so it may be a good time to watch the summary video lecture of this book here. It's on the internet. And there's also a multi-agent video lecture, which I gave the link earlier. There's a YouTube video on that, on this link, and it also includes a demonstration with spiders and flies. Questions here? Okay, so see you next week.